Hello everyone, myself, one second. Hello everyone, myself Kartikeya, a third year EPH student in IIT Roorkee, and today I will be presenting my project, Scintillation Detector Calibration, done under the course PHC 351 Fundamentals of AIML. So let's start with the presentation with the bit overview of my project. So my project is about creating a mathematical model or a mathematical equation using the AIML techniques which can predict the total number of pulse counts recorded by my scintillator detector. Yeah. So proceeding over the objectives of this project, this project started by understanding the theory behind scintillator detectors and how they are used for detecting radiation, followed by parsing the raw text file to obtain the data, then understanding the data, then model training and results. Okay, so let's talk about scintillator detectors. Scintillator detectors are a type of radiation detectors which work by first converting the high energy radiation into lower energy visible flashes, and these flashes are then recorded by the detector and outputted as electrical pulse. And there are four main components of a scintillator detector, starting from a scintillator crystal which absorbs the light and emits, which absorbs the radiation and emits visible photon, the photomultiplier tube which converts the received photon from the scintillator crystal and creates an electrical pulse which then goes to the ADC which converts which detects this electrical pulse and the data acquisition system we are using to record the detector operating conditions as well as the output for the purpose of training our model. Okay, so let's talk about the materials. Let's talk about scintillators. Scintillators are materials which have the property of absorbing input radiation, even high energy radiations such as alpha rays, uh, beta rays, gamma rays, even high energy photons and such. Uh, these materials absorb all these radiations and converts them into uh, visible light or UV light, and this process is called scintillation. So scintillation happens in four main steps, starting by the absorption of my radiation into the scintillator crystal, then the input radiation, the received radiation, then proceeds to excite the electron present in the material over into a higher energy state. These excited electrons then move. These excited electrons then proceed to de-excite into the ground state, releasing photons uh, with energy equal to their band gap, and these released photons are then later uh, given to photomultiplier tube for detection, and these photons are typically in visible or UV range. Photomultiplier tube. Photomultiplier tube is a light sensitive device which converts the input photons it receives from the scintillator material and converts them into electrical pulses for the through a process of electron multiplication, which I will explain. And a photomultiplier tube works by these given main processes, which starts by a photocathode, which is present. I will show it here. A photocathode, which is present at the front of photomultiplier tube, which absorbs the input visible photons and generates a photoelectron. After that, the electron get excited, not excited, accelerated because of high potential difference, then hit the first dynode. So this curved uh, this curved electrode here is a dynode, and a dynode have a very interesting property that it works as both a anode and a cathode at the same time. And how it does that is, a dynode have a potential which is higher than my photocathode and lower than a second dynode which is placed after it. So what happens is, an electron moves from a photocathode and hits the first dynode, As it hits the first diode, the accelerated electron releases some more electrons from the diode, which is now present between the first diode and the second diode. Now my first diode have a lower potential compared to second diode, and all the electrons which were generated by the first diode then now hits my second diode, because it is at higher potential. uh, and now the each electron released by the first diode proceed to create more electrons by colliding with the second diode. So it happens by a process of multiplication. Let's say one electron hit this diode and created four electrons, so this four electron will hit second diode and create 16 electrons, and it process will happen till there are a lot of electrons at the uh, last diode. Yeah, so after repeating the process, the final electrons are then collected at the anode. Uh, so this process of electron multiplication happening at diodes is the reason why uh, scintillator detectors are very good at detecting radiations. Uh, they are very sensitive. Uh, okay, yeah. And my radiation is collected at the anode and then sent to my electron, my ADC, to be measured and displayed as a pulse. Okay, so let's talk about the data set which I'm going to use. So the data set I so the data set which I used for this project was given to me by the Divya Drishti Lab, IIT Roorkee. Uh, and this data set, I'm going to use three input parameters from this data set and one output parameter. Uh, a bit of the data set is displayed here. I will show it more as I proceed towards the code. So the input parameters which I'm using is the time for which the experiment was run, or for which the radiation was allowed to hit the detector. LLD, which is the lower limit discriminant. The lower limit discriminant is the minimum threshold energy which an input radiation must exceed for it to be recorded as a pulse. If an input radiation have energy lower than lower limit discriminant, it will not be get recorded. It will either not get recorded or get discarded as a background noise, or not and not an input radiation. High voltage here refers to the voltage across the photomultiplier tube. So the voltage across photomultiplier tube is actually very high. Like there's a gain of around 100 or 200 volt after each diode. And the count here refers to the pulses which were recorded by the detector, by the final display screen. Let's proceed with the data visualization and correlation. So here I have displayed the total graph of counts versus the LLD, and LLD is actually the most statistically significant parameter to be trained over. Like I will show it as I speak about their correlation. So all all of my three input parameters, time, high voltage, and LLD, we see that the Spearman correlation and p-value, uh, they do not give me any number for time. Uh, so let's talk about this. Spearman correlation is tells me about how related my two parameters are. Let's say it is mostly between 1 and -1. Spearman correlation value of 1 means that they are highly correlated, and if one parameter increases, the other parameter also increases. And a correlation value of -1 is also refers to a very strong correlation, but a negative correlation, which is if one parameter increases, other parameter decreases. Uh, a correlation value close to 0 is weak, which means they are two inputs, they do not have any correlation with them. And p-value refers to whether p-value tells us whether or not the null hypothesis can be rejected or not. Null hypothesis said that any two parameter null hypothesis says that any two parameters are actually statistically insignificant. They are insignificant in the sense that change in one parameter does not affect second parameter, or whether or not null hypothesis can be completely discarded or not is told us by p-value. So let's start. First, I see that time does not have either a Spearman correlation or a p-value. Can occur because, like, a possible reason for this is for all of my processes all of my data set, the same time value is used. Like the experiment was always run for same amount of time, uh, which is very acceptable. The HV here is the HV, the high voltage across photomultiply tube. We see a PMN correlation value of minus 0.11, which means that higher it's a which means that a weak correlation was observed, a weak negative correlation was observed, and a p value of almost 0.09 was observed. Uh, so if my p value is greater than 0.05, it means that null hypothesis cannot be ignored. There is a good chance that the two input parameters are not statistically correlated to each other. So the p-value of 0.09 means there is very high probability that high voltage is not actually related to my output parameter, which is the pulse counts in any way. LLD, however, shows a spearman correlation of 0.45 and a p-value very small, in 10 raised to the minus 13, which means that null hypothesis can be completely ignored. There is good correlation between my LLD, the discriminant voltage, as well as my uh, detector count. Okay, let's proceed to the scaling of my data set. Our data set is usually there's a standard procedure to scale the data set before feeding it to your model. Um, Here I have used standard scaler, which refers to scaling it such that all of my data set comes down to a mean of 0 and a standard deviation of 1. There are other scaling methods as well, like min max scaling, and however I use this particular method. Okay, so next is the training of my model. uh, so for training, essentially I've used three models for prediction. One is SVR, support vector regression. Next is polynomial regression, and an ANN, which is artificial neural network. uh, and for the results here, I've shown the SVR model and how it is implemented in the Jupyter notebook. I will switch to Jupyter notebook as well soon. It is imported from the sklearn library, which is a standard library for any machine learning task. And SVR is a regression algorithm, support vector regression, which which defines a prediction line based on the margin between my current line and all the data points around it. The closer distance between my line and my data points is called a margin, and it is used those margin to optimize the line for a better fit. We are using an RBF kernel, which is a radial bias function. Uh, and upon training this model, we get an R squared value of 0.133 and a mean absolute error of 249. Now our R squared value is a process of evaluating your model prediction. It returns us a value between 0 and 1, and how it works is R squared value of 1 means your model is very good at predicting, and R square value of 0 is that your model is very bad at predicting. So what actually its output tell us that how good your model is in prediction compared to the most basic of the prediction which could have been done, which refers to predicting every value to be equal to just the mean of my data set. Like take the mean of all my data set, and it is my every value, just predict it everywhere. So I mean R squared value close to 0 means it just outputs me a value close to the mean of my input data set, and an R squared value of 1 means it is actually very better in predicting. And the mean absolute error refers to the average out of the absolute difference between a predicted value and the actual value calculated over the test data set. Okay, the second model we have used is polynomial regression. So how polynomial regression works is it starts by moving our data set over a higher dimensional plane. So what happens is, let's say my input parameters are here my input parameters are time and LLD, time, LLD, and voltage. So what it does is it will keep the parameter time, LLD, voltage, and add more parameters, higher degree parameters. Let's say time squared, LLD squared, voltage squared, cube of them, and up to that. So my data set is now moved to a higher dimensional data set. So here we have moved our data set to a higher dimensional using a degree of 12, which is up to the 12th degree polynomial time raised to power 12 as such that. And after dividing our data set, we are training it over a linear regression, because now my data set is at higher dimension. A linear regression is actually essentially a polynomial regression only. Uh, um, then I fit my data set and use it over our test data, and I'm receiving a r squared value of almost zero point 0.9 and a mean absolute error of 110. And we can see that this model is predicting actually way better compared to SVR model. The third and last model is an artificial neural network, ANN, and I have used a model which takes three input parameters. Its input layer have three nodes, three neurons. Then it have two hidden layers of 15 nodes each, and one output node using a ReLU activation function. And ReLU function is just if its input is -1, it outputs me 0, and if its input is if its input is negative, it outputs me 0, and if its input is greater than 0, it outputs me the input which it received. And decay rate is used as 0.05, and decays at the rate of 0.96 per epoch. And after training it for 100 epochs, I received a mean absolute error of 276, which is actually very less compared to poly regression model, and even less than the SVR. uh, okay, so here is the comparison between two models which actually performed way better. uh, it means that two of the better performing models is a comparison. The graph is between the actual counts and not actual counts and predicted counts. So the more values which are along the diagonal of this graph, the better is my model prediction. So let's see, here the 0 0 is here, and so the line along this part refers to a good model. So and I am receiving a lot of, most of my predictions are along this line for polynomial regression model. SVR model, however, is 750 and 700, so line along this, it refers to a good model. So SVR is predicting actually pretty good for lower value of counts, but it actually is failing for the higher value of counts. Okay, so for the result of my project, in my project we saw that a 12th degree polynomial regression showed the best results compared to the three models which we trained. And we also obtained a 12th degree polynomial equation, which gives us the counts of scintillator detectors as a function of its input parameters. I will show the equation now, and as such the main object, which was the calibration of detector, is also completed. Okay. uh, so switching into the code now, we can see that a lot of this code I've already explained during my project. uh, so this data set, I've already passed my data set and converted into a CSV. I will put both the CSV file and the text file as the data set when I submit this project. Oh, before that, we can first see that my project, while I've used only time, HV, and LLD, we can see that the original data set have two more parameters, which is events and run. However, those two parameters were ignored during this project, because the runs here refers to the number of times the experiment was run, and it was constant for a very, like, every time the experiment was done for only one time. And the events here just refers to the index of nuclear event. It's not very significant to the counts. Like, even intuitively, it's not very significant to the counts. Okay, so everything else is explained during the presentation. And here is the final equation which I received. So this is a 12th degree polynomial, and this polynomial ignores the terms which had very low coefficient, which means they do not really contribute very high. So here I can see a constant term into uh, first degree of time into first degree of voltage into first degree of LLD plus second degree of time into voltage, time into LLD, voltage square, and so on goes to the 12 degree, which is V voltage square discrement power 10 and up to 12 degree. So this is the final equation which was predicted by a 12th degree polynomial regression. Okay, and we found that this model and this equation predicted by the 12th degree polynomial, I ran it for the higher degree and a lower degree as well, but the 12th degree gave the best results. Yeah, this, so the 12th degree polynomial is best for fitting or calibrating a scintillator detector. And with that I finish my presentation. Thank you.